to the next talk about, which is a three-part act with David Booker, co-founder and CTO of the National Air Quality Testing Services, who specializes in aerosol physics. And he's going to be joined by Alan Friday, Professor of Computing and Sustainability at Lancaster University, and Iman Hussain, who's a PhD student at Lancaster. So I'm going to hand over to them. I don't quite know the order that's happening here, but I'm in your hands, guys, whatever you would like to do.
Hi there, good to see you all. So I'll be starting off the presentation today, and then I'll be handing over to David Booker.
Thanks, Iman.
So it's been a pleasure to be here and to listen to what you guys have to say. It's been really informative, and I'd love to add to that here with our little presentation, all to do with unlocking the air quality, comfort and energy trilemma. Can you guys see the PowerPoint nice and clearly?
Yeah, it's fine. I can see it well. Thank you.
Brilliant. So we already know a lot about why we need to understand and care about the air. Essentially, it's just as important to us as water and food, but unlike water and food, air is a lot harder to avoid. You can't just take away and say no to stale air. It's often way too late. Now, the government's air quality strategy focuses a lot on outdoor air quality with old-fashioned ideas of smog and pollution in urban areas, but we spend 90% of our time indoors. So perhaps we need to start to think about things a little bit differently. Outdoor pollutants often add to indoor sources, and these increase the health-related impacts of poor indoor air quality. Particulates are a good example of both macro and micro environmental challenges. The current pandemic has highlighted the impact and importance of air quality indoors. Two quite shocking figures. So a 1 microgram meter cube reduction in fine particulate air pollution in England could prevent 100,000 cases of coronary heart disease, 16,500 strokes, 9,300 cases of asthma, and 4,200 lung cancers over an 18-year period. It's an incredibly important issue, and it's not just something that affects people outdoors or down mines. This can happen in our homes and, of course, in our schools too. More recently, people have been using carbon dioxide measurements in built-up areas and internal spaces to start to understand how coronavirus and COVID transmits. Carbon dioxide concentrations above the value of 750 ppm, especially at the breathing level, may indicate that the ventilation is inadequate and that remedial action should be taken. The risk of infection is thought to be increased with exposure time, and we'll be talking a little bit more about that in just a moment. The key thing is that a lot of the ways that we start to clean the air and ventilate the air, as we've been discussing so far, are very energy and carbon intensive. And that's another factor that we need to balance when it comes to air quality, because of course, all this carbon in the atmosphere comes from things like energy, or creating energy that would then go into feeding HVAC and filtration systems. It's almost like a big loop or a cycle. In terms of schools, the average school spends about 55% of its energy on heating, which is incredible compared to the 20% that it would spend on computers and IT. You may think that those would be the other way around, but it's really interesting to see that. Now, this heating is lumped in with the majority heating of the UK, of which 20% comes from fossil fuels and is a massive part of Britain's carbon footprint. The average heating cost per pupil per year is £44, yet significant amounts of energy is wasted out of hours or on empty classrooms. And it's a big shame. Now, all of this feeds into this idea of a triangle that some of my colleagues speaking earlier have spoke about, the idea of comfort, energy, and air quality, how they're all balanced and how it's very difficult to focus on one without detracting from the others, or at least it is now. Comfort is linked to factors including temperature, airflow, and can affect productivity, concentration, and learning. Heating and filtration requires more energy. Building codes, so a lot more recently, have started to increasingly favor less air leakage and good thermal performance. Now, of course, this leads to lower energy costs, but with less ventilation, both mechanical and natural, you get less air exchange, which leads to stuffier environments, which might be worse for your comfort or your well-being in the long term. More recently, this pendulum has swung the other way. A lot of institutions, businesses, and schools have been advised to start ventilating a lot more to reduce rates of transmissions. But increasing ventilation and filtration increases the demand on HVAC as it has to counter for the increased air exchange rate. And this, of course, feeds back into the idea that your carbon footprint and your costs is massively going to be increasing. Balancing all three requires understanding this multidimensional problem of indoor air quality. It's not as simple as fresh air good, indoor bad. Here's a result from a little bit of a test case that the NAQTS undertook. Using our sensors and our devices, we placed a device in an urban classroom just on the outskirts of Reading over the course of the last year winter term. And these results are from the 5th of October all the way to the 16th. Now it's measuring the CO2 level in parts per million in a classroom, and it's quite alarming the results that we got. To simplify it a little bit, we've color coded it. Blue would be considered the baseline, green would be okay, orange between 1,000 and 1,500 is when you'd start to notice a little bit of sleepiness and lack of attention. And between 1,500 and 5,000 is when you're getting serious lacks of cognitive ability, as well as potential long-term side effects from the exposure. Now, I was blessed. I used to work in a school, and you'd often notice that near the end of the day, students would find it a lot harder to struggle and a lot harder to concentrate. And some of that could be linked to this idea of CO2 being built up in schools. Now, BB 101, or Building Bulletin 101, is a piece of guidance released by the government. Essentially, classrooms shouldn't have over 2,000 ppm of CO2 for longer than 20 minutes consecutively. And we can see that this has been the case for quite a long time. What's also quite interesting is by measuring and charting the levels of CO2, we can use the Wells-Rayleigh equation to start to understand the air exchange rate. And we can start to see at what points in the day this is increasing and decreasing. And we can understand perhaps when the energy usage is increasing and decreasing too. Another important bit of information we collected is this idea of level of PM 2.5 across a week in the same school. PM 2.5 is the measurement of particles around 3% of the human hair, and these can cause major havoc if they're breathed in into your lungs. An effective way to reduce transmission of airborne diseases is to reduce its concentration in the vicinity of occupants. In addition to ventilation, filtration can be used. Now, there's no standard for levels of PM 2.5 in a classroom, but the World Health Organization states that long-term exposure over 10 micrograms per meters cubed should not be exceeded, whilst the UK legal limit is 20 micrograms. And we can see that we're above 20, and in fact, we're above 10 quite a few times, most notably between the 22nd and the 24th of September. COVID-19 has served as a wake-up call by focusing on ventilation. The challenges of balancing indoor air quality have become a lot more apparent. We're at a turning point. We have the opportunity to rewrite what IAQ means, to capitalize on the disruption that COVID has created and balance safety, comfort, and energy use. But it's difficult to do that without the right technology. And that's what we're looking to do. We've had quite a few success with using larger sensor arrays so far, but they're a bit expensive and they're hard to deploy and monitor. So we're looking at upgrading these and taking it a step further by using something called the Internet of Things, or IoT. This describes a network of smart devices, utilizing sensors, communicating and coordinating together. We plan on harnessing this technology to deliver actionable and fine-grained insights on the indoor environment at a more affordable price point. There'll be a lower cost of entry and it will be more accessible. Instead of buying one massive device, you can start off with one or two smaller ones and then branch out to more. As they're small and a little bit more inconspicuous, they can be distributed around the school and be scaled and maintained in an easier way. Because they're deployed in such a unique way, they can fit a lot of the interesting and quite nice modern floor plans that a lot of new schools have, with a mixture of wide open spaces and smaller, more close grouped classes. It can deliver more accurate insights with more control over the data collected. We can't really understand what we can't measure. Our goal is to create this kind of modular system that is affordable for all stakeholders to deploy and delivers key actionable intelligence on what the air quality is like in a system. Now I'll be handing over to my colleague, CTO, David Booker. He'll be taking you through a little bit about who we are and what we do in more detail.
Okay, thank you. Can you just acknowledge that you can hear me, that the microphone's working?
Okay, so
National Air Quality Testing Services, NAQTS, was founded in 2015 and is centered at University of Lancaster in their LEC. And the objective of NAQTS was to look and address the issues associated with indoor air quality and the effects of health. Now, we've been doing this since 2015. We didn't forecast what happened last year. But fortuitously, sometimes when you're involved in engineering and science, you have the right equipment in the right place at the right time. So just before the end of 2019, we deployed this V2000 unit that you see in the center of the screen into multiple schools in the UK to monitor 24 hours a day, 7 days a week, the whole range of various pollutants. Unknown to us, we were going to continue to monitor during the first shutdown and then continue to monitor in a limited number of schools following the shutdown when the children returned back to schools. So, indoor air quality with over 1 gigabyte of data. Now, this did not go all that well because we don't understand schools. So we want this partnership. So, for example, how do you communicate? Can you access Wi-Fi? We put GSM modems in the equipment to talk to the cloud. What happened is it didn't always work in the rural environments. So we're really excited to be working with Lancaster University, with Iman, who's going to be leading a PhD on this subject, to look at data management, architecture, mesh networks, whatever the network will be, with the view to do something that is most important. That is to make it affordable and informative. So if you look on this slide, you can see this unit at the top measured everything. It didn't make breakfast for the children, but it might as well done that because we even measured VOCs. We even could tell you when the children were eating their lunch in the school classroom because of the VOCs. So if you go to the next slide, I'll show you what we're really excited to do. We're using COVID as an example of indoor air quality. Now, I was very pleased to hear in some of the other presentations, CO2 does not equal to good indoor air quality. CO2 is affordable and easy to measure. It's fantastic for looking at ventilation rates. And of course, ventilation rates are one of the important parameters in, for example, the Wells-Riley equation, where we're looking at this Poisson probability distribution of being infected. But if it's an airborne particulate, as we show here in this picture, particulate concentrations are also important. So how can we increase ventilation? How can we reduce particulates? So now we look at ventilation and filtration as being possible solutions. But we have to do it in a manner where we can make large-scale measurements in the microenvironment because we cannot assume each classroom behaves in the same way. We also have to understand macro air pollution because, again, the pollution that comes inside the classroom is probably low in terms of the viral load. And when we measure particulates, we just need to remove particulates. So if you go to the next slide, we want to do this in a way which is affordable, which is why we're, again, excited to be working with this team from Lancaster University, who are experts in the management of data and networks and all the rest of it to help us. So we've got a concept of producing a cheaper, less costly equipment that can go into school classrooms that will measure the various parts, for example, carbon dioxide, particulates using these low-cost PM 2.5 devices. And I show here a sort of nerdy example of what the network would look like. But clearly, this is something that we want to be easy, portable, and low cost. Now, if we get this system into multiple schools, we will generate gigabytes and gigabytes of data. That in its own right is not of great value. So we're also wanting to lean on the skills within Lancaster and our own knowledge and others to look at data analytics and ultimately to produce things that I guess the computing scientists use, APIs, application programming interfaces. To the layman like me, that means we got to have this system talk to the building management system, so that the opening a window, turning on a ventilation system is all done in the whole overview of energy and indoor air quality management. So if you go to the next slide. So
Sorry.
we talk about infographics, and I love this example by the simple visualization of the data done on the UK Air Quality Index from a scale 1 to high. Okay, we need to do the same for indoor air quality. Nobody needs to know how many micrograms per cubic meter of all the various pollutants there are. We don't expect school teachers to understand what the World Health Organization thresholds are, but we do want them to understand and know when the air quality is good, when it can be slightly improved on a simple scale. And I think this is also a bit like citizen science. We can tell the students, get the students engaged into these types of projects where not only are we making the measurements, we're doing the analytics, but we're disseminating the information in a way which is usable. Because when we move away from COVID and the acute and sort of chronic effects of COVID exposure and just look at general air quality, it's a long-term issue. So behavioral change is what we really want to look for in the long run. So if you go to the next slide. So stakeholders, I haven't seen some of these slides, so keep going. I don't like all, go on, put them all.
That's okay. So our data collected, as David was saying, is invaluable and can provide a high level of insights relevant to all sorts of stakeholders. From a high level, estate management staff will be able to utilize humidity and temperature sensors to pinpoint areas of repair, as well as highlight any potential building issues. It could also be fed into an API. That means that any sort of HVAC system that the school uses could potentially use the same data to make the cooling and ventilation systems a lot more efficient by being able to respond to things in a demand-based way, saving money and reducing the carbon footprint.
If we can manage time, go to the last slide.
Oh,
please.
of course.
So conclusions are, we would like to get stakeholder involvement. So get in contact with us. Would be interesting to set up a group of people, of experts in the subject matter, to look at how we can disseminate this information. So both Iman and myself, thank you for the opportunity for allowing us to present at this important meeting.
It's been an absolute pleasure.
Yeah, thank you both very much.